I'm pretty sure that the one I did not. I chose you as an alien.
What?
I got too attention that should Yeah, okay.
Because Mr. Sun said it wouldn't have been your fault, because he said that you should just not trust somebody that shouldn't be trusted. So if he
You said take it in.
You can drink. Yeah, it was like one snitched on me and yes, we both had I heard that guy was like 7 straight. Because of 4 food and launch. I remember calling my dad. Dad, I gotta go there a little more. Got mad, so back to how are they gonna know? How's my dad? No, but there's strategy. They're so
Hi, everybody. We're going to pick up where we left off. We're still kind of inside chapter 1, kind of plowing our way through this. Is this where we left off? Did we do this? We did do this one? We did the standard deviation for it. I can't remember because the next day I did the class in a full period and we finished everything, so I don't really remember. Did we talk about the calculator?
No.
Okay. So in this problem, we had just been asked to compute the expectation and standard deviation for this probability distribution. And we had been doing this by hand, basically, or like at least typing it out the entire formula to put into our calculator, which we'll call the same thing as doing by hand. If you know how to enter things, so the calculator will do the computation for you. So that's what we want to take a moment here and illustrate for you guys. So what you'd want to do is you want to enter this probability distribution as 2 lists. List 1 would be your values for x, and list 2 would be the probabilities. And then if you do 1 variable stats, where you're using your list as L1 and your frequency list as L2, so the values for x are your L1 and the probabilities are your frequency. If you input that, the calculator is going to output the mean as your expectation and the standard deviation as your standard deviation. So as long as you're using that probabilities as your frequency list, the calculator can do the expectation and the standard deviation for you. You just have to remember to use the frequency list, or to use the probabilities as the frequency list. Was okay?
Yeah.
And this, again, we've used this frequency list before in the first semester, so this should come as something familiar where like the menus are and where all this stuff lives, right? So there's my standard deviation. So let's say we have some data and we want to convert that into a probability distribution. So our situation says one country published a study about its citizens. One question asked its households to report the number of persons living in the household. And below in the table is the summary of that data. So the first thing we have to take care of is this 7 or more category, right? Which isn't gonna work if we're gonna make a probability distribution. That has to be like a specific value. So in the interest of making this work conveniently, we're just gonna change 7 or more to just 7. Not much really else we can do from the data provided to make it better than that. So we're just gonna call it 7 and be done with it. Was okay? So those will be my x's, the digits 1 through 7. So notice I'm building a new table here for my probability distribution. So I've just completed the x columns. Those are the possible values of my random variable. Now I need to convert these number of households that have one individual into a probability. So to do that, I'm just going to take that 31.1 million and divide it by the 116 million, the total number of households, and that'll turn that into a probability. And I'll do that then for each random variable value. And now we have our probability distribution. Notice that I checked that it was a probability distribution because you see the final column or final row in my table is the total, and the sum of my probabilities is equal to 1. So I know it's a probability distribution. Does everybody feel okay as to what I did to do that? Pretty easy, right? This should remind you of something we did in first semester. Basically, we just created a relative frequency table. We took a frequency chart and turned it into a relative frequency chart by converting the counts into percentiles. See how this all kind of wraps back on top of itself? So if I ask then to find the probability that a randomly chosen household has 4 or more persons, what are the values that our random variable can take for 4 or more persons? I'm pausing here because I'm expecting somebody to try to answer that.
Use add up for 4, 5, 6, 7.
Great, so the values that the random variable can take is 4 or 5 or 6 or 7. When we say or, what operation are we going to be using? Adding, right? So we're going to take the probability of 4 plus the probability of 5 plus the probability of 6 plus the probability of 7. Everybody okay? Again, I'm trying to go through and review these concepts from chapter 8 because I'm guessing you didn't do a lot of math over Christmas break, and that's okay. If I want to calculate the expected value, I'll just take the value for x and multiply it by its probability and add those up for every value of x. So I have 1 times 0.68 plus 2 times 0.33, and so on and so forth. That's our formula for expectation. Right? Same formula we've been using. No big deal. Or what else could we do? Enter the probability distribution into our calculator as lists and do one variable stats. So just like we did before on the previous example, we could use our calculator to calculate this expectation. So again, typed everything into lists, picked one variable stats, ran L1 as my list, and L2 as my frequency list. And output right there, the mean will be the same as my expectation. Does everybody feel okay there? Again, shouldn't remember where all these menus are in our calculator and how to get to these and be fairly fluent at this point in using this stuff. We're just using the same menus and operations that we've been using all through first semester. So this should be old hat for you guys, right? That's why I'm not breaking out the other calculator and like walking through the button sequences here, because this is buttons we've used a lot. Yeah. Sure. If I want the standard deviation, again, I'll use the formula for standard deviation, or I could just look at that output that I just got from my calculator, because if I did it using the frequency list, the standard deviation that output on for my calculator would be the same standard deviation for the probability distribution. So it's pretty easy, right? Okay, what is the probability distribution of the discrete random variable x that counts the number of heads in 4 flips of the coin, of a fair coin? So to do that, let's think about what are the possible outcomes of 4 flips of a coin in terms of the number of heads. Ethan? So 4 heads, right? Or 0 heads, yep. Correct. So my random variable can take the values of 0, 1, 2, 3, 4. What's the part that's going to be difficult to come up with? How many different ways we can get 1 head or 2 head or 3 head, right? Should be fairly obvious that there's only one way to get 4 heads and one way to get 0 heads, right? So to do the counting that we're going to need to do to figure out how many different ways we can get 1 head, 2 head, or 3 head, I'm going to build a tree diagram to kind of model what's going on here. So each branching is going to represent 1 flip of the coin. So here's my first flip, and then my second flip. So each branch gets its separate branching. My third flip, and then my fourth flip. And there at the end, I've consolidated by reading down the branch, what is the individual outcome here. So if I look at the top branch, I got heads, 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 and heads. So that's my 4-head situation. Where I got heads, 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 and tails. That's a 3-head situation. So by doing this, I've enumerated all the possible different ways that flipping of 4 coins could turn out, right? Everybody's good? Okay. What's the probability that the coin flip a single coin flip ends up heads? 50% or 1/2. And tails? 50% or 1/2. Here's the great news then. Regardless of which path we take, the probability is going to be the same because the probability along each branch is 1/2, right? Which is lovely. So I really only need to do this once, and I'll have the probability for each of these. Everybody's good? So if I have heads, and heads, and heads, and heads, and when we're dealing with probabilities means that we need to multiply, so I'm just going to have 1/2 times 1/2 times 1/2 times 1/2, or 1/16. So each of these have a 1/16 probability, or 1/16 as a decimal is 0.0625. it's easier to not write a fraction when you're making these slides in Excel. So I put the decimal there just because the formatting on Excel is not very math friendly. Or not Excel, PowerPoint, whatever this stupid thing is. You know what I'm talking about. All right, so I'm going to start building up my probability distribution. So I've listed my 5 values that my random variable can take. So to get 0 heads, there's just one way that can happen. So there's my probability for that one. If I look at 1 head, there's 4 different ways that can happen. So I'm going to have that 0.0625 multiplied by 4, right? Because I have 4 of them. If I look at 3, there's 6 ways to get, or I'm sorry, if I look at 2 heads, there's 6 ways to get 2 heads. So I have like 6/16 there, or 3/8, or that number. And if I look at 4 or 3 heads, there's 4 ways of that happening again. So 4/16 or 0.25. And then just one way to get all heads. And there's that. Okay. So the hardest part about this was making sure to draw the tree diagram so you can figure out how many different ways you can get 0 heads or 1 heads or 2 heads or 3 heads or 4 heads. Because that turns out to be, the hardest part about this, right? Is making sure you account for that. That like, this stuff can happen more than one way. Everybody's okay? All right, well, that's the end of this show. Let's look at some of these in-class examples and kind of work through some of this stuff together. Sound good? Suppose you have 2 fair dice, meaning all the sides are equally likely to face up when rolled. The first die is a 4-sided die with the numbers 2, 4, 6, 8 on its faces. The second die is a 3-sided die with the numbers 1, 3, 3 on its faces. Let x be the number that appears on the first die. Write a probability distribution for that variable x. Okay, what are the possible values that x can take?
One, 2, 3, 4, 6, 8.
So x is the number that appears on the first die.
Oh, okay. So just 2, 4, 6, 8.
2, 4, 6, and 8, yes. Feel good? How many different ways when I roll the dice can I get a 2? And a 4, and a 6, and an 8. Okay, so they're all equally likely, so they should all have the same probability, right? That probability being
0.25.
1 in 4 or 0.25. Yep. Either way of writing it would be fine. The last thing I'd want to do is check to see what?
That adds 4.
If all the probabilities add to 1. And clearly they do, right? Like, welcome back to 5th grade math. I'm sure 4 quarters is a 1. All right. Says let y be the number that appears on the second die. Write a probability distribution for the variable y. So what are the different outcomes for the variable y? What are the different values that y can take? 1 and 3. Good. How many different ways can 1 happen? How many different ways can 3 happen? 2. So what's the probability of 1? Okay, 0.3 repeating, or 1/3. I'm going to write the fraction here so I don't have to do any rounding. And the probability of 3 occurring? 2/3, or 0.6 repeating. And again, before I'm done, I'm just going to give myself one little quick check that the probabilities add to 1. And they do. Everybody happy? Not too bad, right? Again, you have to think a little bit about what's going on. Like, you have to read the question, understand what's happening, but like the actual nuts and bolts of like doing this is pretty easy. The hard part is reading and understanding, right? Part C says, let A be the total of the 2 die when rolled together. Write a probability distribution for variable A. This is much more difficult, right? So let's draw a tree diagram to handle this. So I'll draw my first set of branching. Is my first die. Does it feel good? Okay. And this will be the second die. Everybody's okay here? All right. This is okay, so my different sums that I can, my different values that A can take, 2 plus 1, 2 plus 5, 4 plus 1, that's another 5. I'm not going to write it twice, right? I'll write here 4 plus 3, that's a 7. 6 plus 1, that's a 7. 6 plus 3, that's 9. 8 plus 1, that's 9. And 8 plus 3, that's 11. Everybody's okay with how I found the values for A? No? Again, A is the sum, so I'm just like figuring out those are the roll, like the numbers that come up on the dice, so I'm just adding them together and looking at the different possibilities. I got some repeats, and that's okay. Not a big deal, right? Okay, so far so good. So now I need to find the probabilities of each of these. A little bit more space here. So the probability of that first getting that 3 is going to be 0.25 times 1/3, right? Which is 1/6. No, 1/12. Right, 1/4 times 1/3 is 1/12. So I'm going to just write it as, I'm not positive on the decimal for 1/12. I think what 10 or 0.067 or 666. I'm not sure. Anyway, it doesn't matter. Here we have 1/4 times 2/3, so that's going to be 2/12. I know I could reduce that, but I'm going to leave them unreduced because it's going to make it easier to check my probability distribution if I have a common denominator across all my fractions. And the IB doesn't care if you reduce or not, so. To get to this 5, I'm going to do 1/4 times 1/3, so 1/12. And then to get to the next 7, it's going to be 1/4 times 2/3, that's 2/12. And then 1/4 times 1/3, that's 1/12. And then 1/4 times 2/3, that's 2/12. And then 1/4 times 1/3, that's 1/12. And 1/4 times 2/3, that's 2/12. Does everybody feel okay what I did there? So to get a 3, or to get 3, just 1 and 12. There's only one way to get a 3. To get a 5, I'm going to have 2/12 plus 1/12, because there's 2 different ways, so I have to add those probabilities. To get the 7, I have 2/12 plus 1/12. To get the 9, I have 2/12 plus 1/12. And to get the 11, I have 2/12. And if I add those all up, I get 12/12. So I'm pretty sure that I got it. Everybody feel okay with what we did there? What's the hardest part? Building out the tree diagram and like making sure everything is counted correctly. But the actual mathematics we did, all we did is like multiply and add stuff, right? Like it was not, there's no complicated algebra. It's just making sure that we understood the situation enough to like build the diagram and get the information we needed out of it, right? So far so good. Part D says find the probability that A is greater than or equal to 5. So which values can the random variable take that are greater than or equal to 5? Five, 7, 9, and 11. Do we agree? Everybody's good? And because it's or, you could be 5 or 7 or 9 or 11. We know that we're going to be adding them. So I have 3/12 plus 3/12 plus 2/12, which is 11/12. Or what else could have you done? Could have done it by the complement, right? And note that in this specific situation, oops, I should say A. That A less than 5 is the same thing as A less than or equal to 3. Or really just A equals 3. Why is that? I wrote it, you believe me, but why? Why is that working? Why is all of a sudden the probability A less than 5 the same as probability of A equal to 3?
Because the only one less than 5 is 3.
Yeah. If I look at the possible values for my random variable A, the only one that's less than 5 is just 3. So the probability A is less than 5 is the same as A is equal to 3, because that's the only possible value that A could take that's less than 5. Is everybody okay with that? So again, either way of approaching it is fine. I just wanted to show you like how quick that could be. Right? 1 minus a 12th. All right. Back in and make this big again. The random variable z has the following probability distribution. Find the value for k. What's the key given piece of information there? So we have a probability distribution. What does that mean? Two properties. All the probabilities are between 0 and 1, and the sum of the probabilities is equal to 1. Which one of those is going to be the useful one to us? Do I want an inequality to solve for k, or an equation to solve for k? I want the equation, right? So I want that all the probabilities have to sum to 1. So far, so good. What type of an equation do we have here? It's like an algebra 1 question, guys. What? Let's simplify things first, eh? Maybe then it'll dawn on us. So if we combine like terms, what type of an equation is this?
Oh,
Not exponential, no. No. Starts with a Q.
quadratic.
It's a quadratic equation, right? Because we have a variable squared.
Yeah.
Is everybody okay? How do we solve a quadratic equation? What are some of the methods we could use here?
FOIL.
So you could try to factor it. It's the F word you're thinking of. FOIL is expanding.
That's the other way around.
I'm sorry.
That's okay. What else could you use? The quadratic formula. Now, which one would we prefer in this situation? You sure? Because that leading coefficient isn't 1. That means you have to do that long factoring method with the grouping and stuff involved.
Oh, I like that one better.
You like that better? I would do the quadratic formula on this. Also, because I'm not even guaranteed that this value for k is even going to be a rational number. It could be some cuckoo crazy thing. So I would probably default to the quadratic formula here. I suspect it will factor, but that's because most people, when they write test questions like this, don't want to give you something insane. But like, there's no reason it couldn't be like the answer could be the square root of, the square root of 0.7 or something, or it's like yuck. Like that's an irrational number and it's terrible, like gross. So I would use the quadratic formula here, although factoring will probably work. Is everybody okay? All right, who remembers the quadratic formula? I love it.
My son.
I love it. And then pop goes the answer, right? Look, you know what though? Like it works. He's got it. That was perfect. It was the exact formula you needed.
You can't teach that on the video.
You can't imagine the
It will be in the formula pad probably. All right. So we have 4 times 8 times -1 is -32. 2 squared is 4. 4 minus a -32 is 36. Square root of 36 is 6. Is everybody okay with what we got there? So what's our answer? What's the value for K? We keep both of them?
What's your?
No. Very good. Why not?
Can't be like the
Why can't it be negative?
probability.
The probability distribution. The probabilities have to be between 0 and 1. So we for sure discard that solution. Now, are we positive that like 4 times K squared is going to be a number that's between 0 and 1, or might it be bigger than 1? Should we check? Probably should check at least, quickly. So obviously these two are good, right? Because 1/4 is between 0 and 1. 1/4 squared is 1/16. So that's going to be good, right? 4 times 1/4 is going to be 1 times another 1/4. That's good. And then 3 times 1/4 is between 0 and 1. And then times another 1/4 is still going to be between 0 and 1 because you're multiplying by something less than 1. So it's just going to get smaller. So we're good, right? Now you could check those computationally on a calculator. You don't have to reason it out in your head, but have a calculator it's all the way over there so far. Everybody feel okay though? Okay. The big takeaway is remembering to discard the negative and check to make sure that when you plug the K in, you're getting valid probabilities. Okay. The random variable Q has the following probability distribution. In addition, we're told that 4 times the probability that Q is less than or equal to 1 is equal to 5 times the probability that Q is equal to 3. Find the values for A and B. So again, what's the first key piece of information I'm given? Probability distribution. What's that allow me to do? Same thing as before, right? When you look at this equation, though, what is the issue? We have 2 variables in one equation. Can you solve that? No. What am I going to need? I need a second equation that includes A and B so I can make a system of 2 equations to solve. Everybody's good? So if I clean this guy up a little bit, like that, how am I going to get that second equation? Well, the problem gave us some other information. Have we used that other information yet?
No.
What do you think? Think that's going to be what I need? Probably. All right. So 4 times the probability that Q is less than or equal to 1. What values could Q take if it's less than or equal to 1? 1 or 0. So the probability that it's 1 or 0 is going to be A plus 4A. We have 5 times the probability that Q is equal to 3. What's the probability that Q is equal to 3? 2B. So if I clean this up here and simplify things, I have that 20A is equal to 10B. Those two together are going to form my system of 2 equations that I'm going to use to solve for A and B. Does everybody feel so far so good? Okay. I would probably do this via substitution because we have that 20A is equal to 10B. That's pretty easy to handle. If I divide that equation both sides by 10, I get that B is equal to 2A. So I can substitute into this equation. And replace the B with 2A. 6A plus 4A is 10A. If I divide both sides by 10, I get A is 1/10. And then if B is equal to 2A, I get that B is equal to 1/5. And I'm done. Now, technically speaking, what should I still check? To make sure that those all give me valid probabilities. They do. Here, because I'm not getting more than one solution for A and B, I'm pretty confident that it's going to be okay. But I should at least give like a little passing glance. Since both of those fractions are smaller than like 1/4, I know I'm going to get valid probabilities out of everything because the biggest thing is 4A. So as long as the fraction is smaller than 1/4, I'm going to be fine. Get something between 0 and 1. All right. So it now asks us to find the expectation of A, going back to example 1. So how do we find expectation? It's the value of the random variable times its probability summed for all possibilities, right? So let's go back and look at random variable A. That's this guy that we built over here. I'm just going to do it on the side rather than tracing back. Is that okay? And I'm going to write it out, not actually do the computation because I'm looking at the numbers and I don't like the looks of it. I like the cut of a jib there. So 3 times 1/12 plus 5 times 3 12s plus 7 times 3 12s plus 9 times 3 12s plus 11 times 2 12s. See, 3 and 15 is 18, and 21 is 39, and 27 is 66, and then 22 more would be 88 12ths or something, maybe. I don't know. Arithmetic's hard, guys. Feel free to check it if you want. Or what else could you do? Enter the datas into the values for the random variable and the probabilities into a list on your calculator. Do the one variable stats on it, right? You don't feel like doing the formula, or the problem doesn't require you to do the formula, or even it's just like I'm going to write out the work, but rather than typing that all into my calculator, hoping that I don't make a mistake there. I'm gonna type it into lists and have the calculator get the final answer after I write out the work. You know, like whatever is fine. Personally, I'm about that life where it's like, I'll write out the work and then use the calculator in a more efficient way than actually typing in what I wrote down. All right. Wants us then to find E of Z. So we got to go through and compute these probabilities. So we're told K is 1/4. So I went and computed those probabilities. And then E of Z, or the expected value, is that. And that number could come out to be negative. Looking at it, I've got a couple of negative terms there with pretty large probabilities. So if that comes out to be a negative value, I won't be terribly surprised. Although I guess looking at it, it shouldn't be. Is that 11/4? That's 8/4. Yeah. Yeah, so anyway, whatever. And then the last one wants E of Q. So again, I'm going to come down here and plug this in. So I have 4/10, 1/10, 1/10, and then 2/5. Pretty good. That look good to you guys? What do you notice I did there?
So 0.
Yeah, why did I skip the first value for the random variable?
0 times.
Because it's 0, right? 0 times anything is still 0, and 0 plus the thing doesn't matter, so. Now, if you wrote it in there, is it wrong? No. I'm just trying to be sneaky and see if you guys are paying attention. How awake you are at 8:35 on a Thursday. Nicole's like, I'm gonna have another drink of coffee here, so apparently not awake enough. All right. Last example. How many of you guys are internet gamblers? You should be if you're under 18, so that's not supposed to be doing that yet. If you are, though, this is the kind of way you should be thinking about all of your gambling. So let's read this problem. It says you buy $10 worth of raffle tickets. You can place them in various drawings worth $20, $50, $200, $500, and $1,000. Let T be the random variable, which represents the amount won on each ticket. T has the probability distribution given in the table below. So determine the probability that T is equal to 0. How do I do that? Yeah. Why is that? Because it's a probability distribution, right? So if we call this guy X, we have X plus 0.15 plus .055 plus .011 plus .0025 plus .0006 is equal to 1, and we just solve for x, right? Anyone want to be so kind as to crank that out on the calculator? I think we're probably going to need it for the next step to actually have the decimal there. Don't all jump at once when I ask somebody to crank that out on their calculator so we actually get the decimal. I want you to strain your poor little fingers here.
0.2191.
0.2191. That doesn't seem right.
I'm not. It's equal 1.
I mean, I think it's going to be 0.8 or so, something. I'll do it myself. Thanks, guys. Don't mind me.
Oh, you minus that.
Oh.
Is it wrong?
How about 0.7809? You forgot to subtract it from the other side.
You have to just minus.
Oh,
You have to do algebra there.
oh, I was doing it before we did that, so it's fine for X.
That's okay.
It's okay.
It's okay.
Everyone makes mistakes.
You misunderstood what I was asking for. We'll let that slide.
I was just waiting for the test.
You're just all right. Part B says determine the expected value of t and interpret that meaning in context. Okay. I'll write it in this time because I don't want to confuse anybody. So I will put the 0 there. Do I need to do it though? No. Okay. Got 9.8. What does that mean now in the context? So what is T representing?
The money we want.
So 9.8 means we'd expect to win on average $9.8. How much do we spend? 10. What do you think? Should we play?
Yeah. Only needs 27.
That's how casinos work. That's why you don't see casinos going out of business. Because the longer you play, the more you lose. Right? So, like, if you are planning on gambling, you need to think about, like, what is the expected value here in this bet I'm about to place? If the expected value is bad, do not play for a long time. You want to make a calculated wager and be like, okay, I'm going to try to get in, make some money, and then leave. But the longer you stay, the more you will lose. All of these gambling companies have teams of mathematics PhD students, like running the numbers and analyzing the risk involved for the casino and making it as profitable as possible for the, for these gambling corporations to stay in business. And the sports betting is worse. The reason why is that if you've shown a ability to make intelligent wagers, they're just going to cut the amount that you're allowed to bet until it's basically negligible. So if you continually place bets where the spread moves in to where it's favorable for you, they will just cut your ability to bet to basically nothing. So that we don't want smart gamblers. We want dumb gamblers. We try to force all the smart people out. Anyway, everybody feel okay with what we did here today? I think let's just it's 20 minutes. What do we want to do? Should we start the next thing?
Sure.
The other class.
No.
Well, you guys are already behind. How many slides is this one? Where does it tell me? 24?
So we got the half.
Yeah, let's stop. I don't want to do this yet until you've had a chance to attempt this set of homework, because it's going to overlap in ways that I don't think is going to be helpful.
There's like intervals.
What's that?
There's intervals of like history.
In the homework set?
Yeah.
Yes, there will for sure be histograms. But that's just basically graph probability. Whatever. Okay. So next time, so we've talked about probability distributions in general. In the next 2 lessons, we're going to look at 2 specific probability distributions and how to use those. And talk about like what needs to be true for us to use that particular probability distribution to model our situation. Krish?
Do we also submit the A-class exam?
No, that's what we just did together. So the in-class example is not a homework assignment. I've realized now, so someone else has asked me about this also.
Yeah.
I've formatted the agenda in a way that is misleading. I'll fix that in the future and just say like 4-2 notes and in-class examples and then comma page blah 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 number 1. So it doesn't look like it's part of the homework.
Yeah.
So I see now why you're the second person to ask about this in 2 days. So no, the in-class examples we just did together, you do not need to do those. That's more of an agenda item for me than it is a homework assignment for you. The homework assignment is just page number and the 1 through, I don't know, 17 or something.
What is a CDF?
Cumulative distribution
Okay.
function is the CDF.
Yeah, I just can't read it.
Yeah.